Hi, I'm Steve Sobek, owner of amysflashcards.com. The purpose of this video is to introduce you to graphing various types of functions on a TI-84 graphics calculator, to show you how to modify the line type, and if your calculator has color capability, to be able to change the colors of your functions as they are graphed, and to understand what is meant by a suitable viewing window and some tips for finding that window. Now, a suitable viewing window, this is a concept that's going to be developed throughout this video lesson. But as a quick snapshot of what I mean by that is, if you have a function graphed, we are often concerned about where this graph intersects the x-axis, okay, the x-intercepts. So we would want our viewing window to show the x-intercepts. In other applications, we're concerned about relative max and minima points. So where the graph bottoms out. Now, of course, when I call this a relative maximum point, it's not the highest point. There's many points higher than that. But relative to the points to the left and right, this is higher than they are, and so that's a relative maximum point, and this is a relative minimum point. So we would like to see our viewing window show those relative max and min points. Sometimes we have multiple functions graphed on the same coordinate plane. Here's another function, for example. When we have more than one function graphed in the same plane, usually our primary concern is, where do these graphs intersect? For example, right here. We would want our viewing window to show where those lines intersect. So that's it in a nutshell, and we're going to continue to develop that concept as we go through various examples. All right, let's delve right into example number 1. Okay, as you can see here, our first example, y is equal to 2x minus 4. We call this a first degree polynomial function. It's also referred to as a linear function because the graph of this function is a straight line. We observe that the intercept, the y-intercept, is -4. So down here at -4, it's going to hit the y-axis. And it has a slope of 2, or 2 over 1. So the rise over the run is 2. So it's rising twice as fast as it moves to the right. So we're expecting a graph that looks something like this. So how do we make the calculator graph this function? Well, over here on the calculator, we want to first click the y equal to button. And under y sub 1, we're able to notice that we have the ability to graph many functions, but we're going to, under y sub 1, type in 2x minus 4. So let's type 2x subtract 4, enter, and then I'll hit the graph button, and momentarily we'll see that function being graphed. Now on your calculator, as you're ticking along with me, and I hope that you have your calculator with you and that you're doing this with me, your initial window may look different than this. For all the graphs that I do today, I'm always going to begin with the standard window. The standard window is a window that spans on the x-axis from -10 to +10, and from -10 to +10 on the y-axis. The quickest way to obtain that standard window is to click on your zoom button right here and choose number 6. Number 6 is the standard window. So zoom standard will be number 6, so click on a 6, and then your window will look just like mine. Now, some people might look at that and think to themselves, you know what, that doesn't look like it has a slope of 2. It looks almost like the angle of elevation is 45 degrees, almost like a slope 1. My little rough sketch here looks more accurate than the calculator's graph. Well, the reason it doesn't look like a slope 2 is because the calibration on the horizontal axis is different than on the vertical. See how close the notches are on the vertical axis compared to how spread out they are on the x-axis. If you wanted the calibration to be equal, then we have what we call zoom square. Click on the zoom button and choose number 5, zoom square, and it will increase the minimum and maximum values of x so that each notch is equally spaced as is on the y-axis, and that looks more like a slope 2. Okay. We also want to be able to change the color of the graph, and so let's go back to the y equal 2 button and here's your left arrow key, and move this over top until this portion of the window is highlighted, and hit the enter key, and out pops a little window that enables you to change the color. If you click your right arrow key, we could make it a red, black, magenta. Hit your down arrow key. You could change this to hit your right arrow key, and you could do shading for whenever you're doing inequalities, and dotted lines of various types, a skinnier line, and then back to the normal line again. Let me just hit the down arrow key to highlight the OK button, and then hit enter, and I'll hit graph again, and you'll see that the color should have been changed. There's a magenta graph. All right. Let me go back to y equal 2 again. If you highlight the equal sign and hit enter, and then move to the right, notice that if you hit the graph button, watch what happens. Nothing. It doesn't graph. It kind of deactivates that particular function. That's useful to teachers who want to type in all of their functions, maybe use all of these functions and have them all already typed in, and then just deactivate it and then activate each one when they're ready to use them. I'm just going to pause the video when I'm ready to type in new functions, so I'm not going to invoke that particular feature today. So let me reactivate that, highlight that, hit enter, and let me go back into the color and restore that to the blue color. Oops, there we go. And hit the down arrow key to highlight the OK button. And then back to the start. And this is how we saw it at the beginning. All right, so there's our first function that we graphed, a straight line linear function, y is equal to 2x minus 4. Okay, suppose the next thing we would like to do is to graph a second function, y is equal to opposite x plus 21, in the same coordinate plane as the first function that we've already graphed. Notice that I've done a zoom 6 to get returned to a standard window. I'm now going to hit the y equal 2 button, and we're going to hit the down arrow key. We want to enter the second function as y sub 2. Okay, these are subscripts. Okay, so we'll go down 1, and let's type in opposite x. Remember that your negative sign is down here beneath the 3. Don't use subtraction for the negative sign. Okay, opposite x plus 21. And let's hit the graph button. Graph button is right up here. And there's our first function, same as before. And the second function we don't see. All right. Does that mean that this function was too difficult for the calculator to handle? No, it just means that the graph of that function is outside of the current viewing window. We have a bad viewing window for this particular system. Now, if this rectangle represented the current viewing window, then Let's use what we know about linear functions to help us to change the window to something that would be more suitable. We know that the y-intercept is positive 21. That means the point 0, 21 is one of the points on that line. Well, you see, 0, 21, that would be way up yonder, even higher than this. Okay, but I don't want to run into the functions. And it has a slope of, this is like a slope of -1. Okay, that means it's going to be going downhill. So it's generally it's going to look something like this. So if we want to see that function, we understand that we need to change the maximum value for y in the viewing window. We haven't changed the viewing windows yet, so over here under, oh, we have with the zoom button, but we haven't manually changed the window yet. So we hit the window button, here it is. You could see that I'm at the standard default window, -10 to +10 on both axes. Here's y maximum right here. That's what we desire to change. Hit your down arrow key to highlight, whoops, too far, y max. And let's increase that to, let's see, we have to go up at least to 21. Why don't we go to 25? Type 25, hit enter. And then hit the graph button again. And here we can see the second function is graphed, and we could see the intersection of those two functions. And suppose that this particular application, that was our primary concern, then this would be a suitable viewing window, even though it is not showing the x-intercept of the red function. But if the primary concern was the point of intersection, this is good. We would stop right here. Okay, for our third example, suppose we would like to graph this quadratic function. This is a second-degree polynomial function. Now, over here in the y equal to, if you hit your y equal to button, we need to show you how to get rid of the previous functions. I got rid of y sub 1 already, but I left y sub 2 here so I could show you how to get rid of that. We're going to hit our down arrow key to move down to y sub 2, and then hit the clear button, and that wipes it out. Let's hit the up arrow key again to get up to here, and let's type in this function. Okay, opposite x squared plus 6x plus 16. And go ahead and hit the graph button. Again, I did a zoom 6 to restore the window to the standard window from -10 to +10. And some students might look at that graph and say, whoa, we typed in one function and yet we see it looks like there's two functions here. This line here and this line here. But those who've already covered quadratic functions in their math class, you know that a quadratic function is not a straight line. The shape of a quadratic function is a parabola. And let me get my pen operational here. And parabolas look kind of U-shaped like this. And then some parabolas are upside down. Okay, so we got some parabolas look like that. It's not the best drawing, but looking at our particular function, if we want to discern which of the two types of graphs we have in front of us here, if we look at the coefficient of the quadratic term, the term of the highest degree, it's a -1. If it's negative, which it is, see, right there, then we know that the parabola is upside down. It's a parabola that faces down. So this particular, what we see here in a viewing window is part of the parabola. Okay, we have a viewing window that looks something like this. And we're just not seeing the top of the mountain, so to speak. All right, so again, we have used our understanding of quadratic functions to help us quickly select a better viewing window. We need to increase Y max again. So let's hit the window button. Let's see, about how high do you think we should go? Maybe up to 20. Let's go to Y max. And let's type a 20 and hit the graph button and see if we got to the top of the mountain. Not quite. Let's bump it up to 30. Go back down here. Sometimes it takes a little bit of trial and error. And I have some other tips that will speed up that trial and error process when we get the more complex functions. But I think we're going to cash in here with positive 30 for the maximum value of Y. Hit the graph button again. And there is a nice viewing window for this quadratic function. The shape, it's parabolic. And we're showing the maximum, the relative max here, which is actually the absolute max, and we're showing the x-intercepts. Good viewing window, quadratic functions. Okay, our next example is a third-degree polynomial function. We could see that the highest exponent on the variable here is a 3. We call third-degree polynomial functions cubic functions. I've already reestablished my viewing window to be the standard window with a zoom 6, and I've typed in the function here. Go ahead and type in the function as you see it here. Recall that the cube to cube x, I obtained that from the math menu, although I certainly could have used the caret over here for exponentiation, either one. And restart the video when you've caught up and typing that in. Now that you've caught up, let's go ahead and hit the graph button and see what this looks like. There it is. Okay. Now I'm going to pause and capture that screen and bring it over here. Okay, inexperienced students will look at this graph and think to themselves, well, that's a pretty decent viewing window. It doesn't appear to have any x-intercepts, and it looks as though our graph includes a relative maximum point right here. But those who have already studied third-degree polynomial functions, cubic functions, know that that's not the whole story. This function is not a parabola. A third-degree polynomial function, if it's going to be one of two things. If it's starting from down here from below like this and coming up, then it's possible that it's going to finish up here, because it's going to, if it starts from below, it has to finish above. Alternatively, if it starts from above, let me make that invisible. If it starts from above, for example, if it came down like this and came up, it's possible that it then finishes below. Okay, but there are always going to be different directions, the starting and ending points for these cubic functions. So we need to expand our window. Now, let's also utilize something else that we know from just looking at the function. The leading coefficient is positive 1/9. If it's positive, then which of those two scenarios would apply to this particular function? Not this one. Let's go back. It has to be this case. For the very extreme high values of x, it's going to be rising upward. It's going to be shooting for the moon. So this is what we expect. Consequently, our viewing window has to expand in which directions? Obviously, we have to expand to the right to see this coming back up. So we can see the other x-intercept over here. And also, whoops, also we need to expand down so we could see this where this bottoms out. Okay, so we're concerned about this relative minimum, and we also want to see this this intercept over here. So we're going to have to go to the right, and we're going to have to go down. Not exactly sure how far, but maybe let's start with a guess and see what happens. Hit the y equal the window button, and x maximum is right here. Why don't we try 25 and see where that gets us. And let's go down to y minimum. We're going to change the lower value of this function here. And why don't we try negative 30 and hit the graph button and see if we're able to see more of the graph. Okay, looks like our maneuver on the x-axis was adequate, plus some. We've gone far enough to the right, but we didn't go far enough downward. It looks like, let's see, 1, 2, 3, 4, 5, 6, 8, 9, 10, 11. When x is 11, it looks like it's going to be bottoming out somewhere around there. I could continue to use, just trial and error. Okay, but here's another tip for knowing how far down to go. In my last video, lesson 1 on using the graphics calculator, we introduced you to the table feature. I'm going to invoke that at this time. I'm going to hit second table. I'm going to delete the current values that are here. Those are values that I've used from the last example. And I'm going to plug in values around, 8, enter, 9, enter. It's substituting in those 8s and 9s, and it's evaluating and showing me the y coordinates. And I could see, well, I'm glad I did this because it's going pretty far down. It's already at negative 75. Let's try 10 to see if it's going any lower. Negative 80. Let's try 11. I think that's where, pretty close to where it's going to bottom out. 12, let's see if it starts to come back up. No, it's still going down. Let's go to 13, and it's coming back up. Okay, so why don't we go negative 90 so we could see the bottom of this graph. So from very quick, rapid fire substitutions using the table feature clued us in as to how low that function is going to go, and thus how low we need to set for y minimum. Negative 90 seems like a good value. All right, so let's go down here. Let's hit the window button and toggle down to y min. And let's try negative 90. I wouldn't blame you for using negative 100 just to make sure that we, hit the graph button. Very nice. This is a nice suitable window for this cubic function. We don't have to be concerned about this graph coming back up over here. We know that third-degree polynomial functions can change directions no more than twice. It's already changed direction here and here. It's changed directions twice. It's not going to change directions again. This is a nice viewing window, except for maybe this y-axis has so many notches in such close proximity that it looks like just almost like a fat line. Typically, whenever we expand our window so far downward or upward that it would be advantageous for us to also make one other change to the window, and that would be y-scale. Y-scale, Y-C-H-L, is where we can dictate how far apart these notches are. They're too close together at every unit. Maybe put a notch at every 10 units. Yeah, sounds like a good idea. Let's go down here and change y scale to 10. And hit enter and hit graph button again. And now, we understand now that each of these notches represents 10. Here's negative 10, negative 20, negative 30, negative 40, negative 50, 60, 70, negative 80, and negative 90. And this graph bottoms out somewhere between negative 80 and negative 90 on the y-axis. All right, so there's a nice viewing window for our cubic function. Okay, here's our next example. Here we have a 4th degree polynomial function. We could see that the highest exponent on the variable is a 4 here. We call these quartic functions. And I started to type it into y sub 1, but I thought maybe I'll pause here and remind you how we can get this raised to the 4th power. It's this caret right here is our ticket for accomplishing that. Click that one time and then type a 4. And then hit the right arrow key to get out of the exponent. And then we can proceed with the rest of this. Minus 2x raised to the 3rd power. We can obtain that from the math menu. Math. And we could see number 3 is cubing something. So hit number 3. Plus x squared. Here's x squared. No wonder. Plus 9x. All right, so there, go ahead and pause the video until you catch up with that, and then continue. Do a zoom 6 if you haven't already restored your window to a standard window. I'll do the same thing here. Zoom 6 so that we'll see the graph of this on a standard window ranging from negative 10 to positive 10 on both axes. And here we can see a graph. And I'm going to capture that window and bring it over here, and then I'll restart the video. All right, here I've copied the graph down here. And again, those students that perhaps have never covered quartic functions before might think that this is a good viewing window. Those who are more experienced students or those who've already covered quartic functions realize that that can't be. That is not a good window. 4th degree or any eventh degree polynomial functions, they're going to, for extreme values, extreme small or big values, are both going to head the same direction, either both up or both down. 4th degree functions will change directions no more than 3 times. This has already changed directions twice. It's going to change directions one more time. One of 2 things is going to happen. Either this function is going to continue up, change directions, and come down here somewhere beyond, outside of the current viewing window, which means we're going to have to increase y max and have a lower value for x min, if that was the case. Alternatively, if the graph, if this is going to go upward, then something like this, and that goes upward. Okay, then both of these graphs are shooting for the moon, heading upward for their extreme values. Then I need to decrease y on the y-axis, y minimum, and I have to increase x max. All right, from what we know about quartic functions, which of the 2 situations is appropriate to, for this function? Well, it's, again, we ascertain that from looking at the coefficient of the term of the highest degree. 1/8 is positive. If the coefficient of the term of the highest degree is positive, then we know that extreme values for x are going to be shooting upward. This is the case for this function, which means we need to decrease y min and we need to increase x maximum. And again, maybe perhaps we could use our table feature just to see, maybe fire in something like a 5, 6, 7, 8, just to see how low we need to go. All right, so let's go back over here and hit the second table. All right, well, we already, maybe this will be adequate for us. The values that I already had in here for x from the last example. I could see it's getting pretty doggone low. The lowest to see here is 12, and then it's starting to come back up. So negative 612. Maybe I'll go to negative 700 based upon what I've observed in the table. So let's hit the window button, and let's hit the down arrow key to highlight the Y minimum. And let's type in negative 700, being very careful to use the negative sign beneath the 3 and not the subtraction key for your negative. And perhaps for Y scale, let's enter to accept that, and go down to Y scale, and perhaps at every 100 units we could put a notch. That seems appropriate. And let's go to X max, and we saw that that was bottoming out around negative 12. So let's go up to say 30. That would seems like that would be playing it safe. We want to be able to see the x-intercept, see it come back up and pass through the horizontal axis. All right, let's give that a shot, and let's hit the graph button and see what that looks like. Okay, a little overkill with the positive 30. Looks like we could have easily gotten away with 20 on that. And if we increase Y max, I think we'll have a nicer viewing window. So let's go back. Again, finding a suitable viewing window is partly involves some trial and error. Make some observations and make some adaptations based upon what we've seen. Let's crank up Y max like we said. Go down here, Y max, and maybe let's use 200 for Y max here. And let's come back up to X max, and I think 20 was more than sufficient for that. And let's see, Y min. Oh, I kind of forget. I think negative 5 would have been adequate for that based on memory. Let's graph that and see what that looks like. All right, now we could, that's a decent viewing window. We could see where it bottoms out if we want to find that that minimum point, and that, of course we do all that in another video. Finding the x-intercepts, that's all in videos to come. Okay, all we're concerned about today is graphing functions, changing the color and the type of lines we have, and also finding suitable windows for viewing this function. All right, and it's subsequent. Make sure you tune into the subsequent videos to see more application and how we attack these graphs and find out all these other things. That's a good window right there. But suppose, here's something I haven't shown you yet, another type of a zoom that I think sometimes you'll want to use. Suppose we want to know what's happening right in here. We want to zoom into that particular area. There's a certain type of a zoom. Hit the zoom button. Call it a box zoom, where you can designate the top left corner and the bottom right corner of a box, and it will zoom into that box. While we're here in the zoom window, let me just briefly mention zoom in. Number 2 is it just zooms in, and number 3 zooms out. Those people who don't have a lot of knowledge about what this function looks like, they're not sure you're supposed to go more down and more to the right, and they think maybe you have to go to the left. They don't know anything. They just zoom out until they see something. And so I don't generally, I sometimes use that, but not as often as the more inexperienced students would use that. And we already used zoom decimal. Zoom trig is something that when you get to trigonometry, if you're in radians, then you'll have a smaller viewing window because 2 pi would be equal to like 360 degrees. And so if you're in degree mode, it's going to span zoom trig is going to take you from like negative 495 to positive 495 to make sure that you could see a couple full cycles of your periodic trigonometric functions. But we're focusing, I just want to focus on the box zoom here, number 1. So we're going to choose number 1. And we've got this blinking plus sign here that we're now going to move around. First, let's move it to where we want to designate as the top left corner of the graph. So let's hit the up arrow key to start moving that up. And let's move that to the left. Okay, let's get going here. Don't want to spend too much time with the box zoom. Okay. Let's say right about there. And hit enter to accept that as the top left corner of your zoom box. And now let's hit the right arrow key and designate the bottom right corner of your zoom rectangle. Let's now hit the down arrow key to go down. And now we have a little rectangle here. And as soon as we hit the enter key, it will zoom in to that little box or rectangle. Okay, let's hit enter. And it zooms in. Now we can see what's happening close up in that particular region. Maybe the implicit domain of the variable of that particular word problem focuses in on that particular region, and all the other intercepts are outside of that range and we're not concerned with them. And so this would be a nice maneuver to pull. A nice box zoom comes in handy more often than you might think. So there's a box zoom. I wanted to show you that. And that's good for the fourth degree polynomial function. Let's move on. Okay, let's summarize what we know about all odd degree polynomial functions. We know that for extreme values of x, the extremely small values compared to very large values, it's going to move in totally opposite directions. If extremely small values of x produce very high values for y, then regardless of what all happens in between, eventually it's going to shoot downward. If it shoots upward at the beginning, then it's going to shoot downward at the end. If it starts very low, then of course it's going to end very high. What about even degree polynomial functions? With the even degree polynomial functions, like our quadratic functions and our quartic functions, and 6th degree and 8th degree polynomial functions, they're going to end the same way it begins. If it starts above, despite of all the wiggle waggles it might do in between, eventually it's going to shoot upwards. Okay, something like that. If it, let me delete that. And if it starts from below, then it's going to end downward. And of course you can look at the coefficient of the term of the highest degree to determine which of the situations that you have for that particular function. There's a quick summary on odd and even degree polynomial functions. Okay, let's say a word about exponential functions. I need to remember what my wife told me. She said if your movie's too long, no one's going to watch the whole thing. So I need to, let me just briefly say a few words about some exponential functions, trigonometric functions, and some rational functions. An exponential function like y is equal to 2 to the x power. Let's go ahead and type that in, 2 raised to the x power. And let's zoom 6 that to get a standard window. And let me just remind you a few things about it. This can be considered like an exponential growth function. I'll capture that window and put it down here and continue. Okay, I've copied the exponential function here. Remember, this is for those who've already covered exponential functions. I'm not teaching exponential functions to you, by the way. I'm reviewing a few things for those who have already covered exponential functions. All right, don't be frustrated if you've never studied exponential functions. Don't expect that you're going to pick up everything that I'm saying here. I'm reviewing for those who've already studied them. All right, and on the other side here, we can see that the graph becomes asymptotic to the x-axis in this case. It looks like it's going downward, but it keeps going downward forever, but it never reaches the x-axis. Remember, when you put in a negative 5 for x, 2 to the negative 5th means 1 over 2 to the positive 5. 1 over 32. 2 to the negative 6 is 1 over 2 to the 6th, 1/64. We put in negative 100. It's going to be 1 over 2 raised to the 100th power. And that's going to be a very, very small number, but it's still a positive number. And 1 over a positive number is going to be positive. We're always above the x-axis. We're getting closer and closer to that line. We call that line an asymptote. And generally we depict that whenever you're sketching a graph on your paper. We depict that with a hyphenated line. Okay, so there's our first or types of graphs that include asymptotes. If it was a decay function, then it would be going downward, would still have that horizontal asymptote. So there's a quick snapshot at exponential functions, what to expect, and that helps you to select good viewing windows for your exponential functions. Let's move on. Okay, let's say a quick word about logarithmic functions, such as y is equal to the log of x. Let's type that in for y sub 1. Here's your log button. This, of course, is log base 10. And here's x, and we'll close the parenthesis. And do a zoom 6 to get a standard viewing window. I've already have one, so I'll just hit the graph button. And this is what is displayed. I'll copy that over here and make some comments. Okay, here's a sketch of the logarithmic function y is equal to log of x. And those of you who studied logarithmic functions and remember that the logarithmic functions are inverse functions of the exponential functions. Consequently, their graphs would look like reflections of the exponential functions about the line y equal x. So where we had horizontal asymptote in the exponential functions, we will have vertical asymptotes in the logarithmic functions. So there's a vertical asymptote here. I'll designate that with a, if you could tell, that's a dashed line, very, very sloppy dashed line. I'm trying to go straight down. And I'll change colors here, and then this graph comes over here and continues downward forever. It gets getting closer and closer to that asymptote without ever actually reaching that. It never crosses over that vertical asymptote. So and this continues to rise over here. That's your typical logarithmic function. And remembering what they look like will help you to select suitable windows whenever you're graphing logarithmic functions. Good enough for now. Okay, let's say a few quick words about trigonometric functions, such as y is equal to the sine of x. Let's type that in over here. Our sine button is right here. It gives us a left parenthesis, so after we type in our x, we'll need a right parenthesis to close that. And let's go ahead and graph that. And here we have the graph of y equals sine of x. And those of you who covered trigonometric functions, then let me just remind you that these are periodic functions. They repeat over and over and over again. And I guess the tip that I would want to share with you is the window that you select for a suitable window. This would be suitable here, although I might want to, bump my y max and min down to 3s. No big deal. Maybe real quickly. Let's go with -3 for the min, +3 for the max, and that might make that look a little bit better. But that's fine. Notice that I'm in radian mode. If you're in degree mode, then we need, remember that the period of the sine function is going to be 360 degrees. So we need massive values for x max if you want to see a full period. All right, let's click mode. Let's come down here to highlight degree, hit enter, and then do a zoom trig. And in degree mode, it's going to go like 495 to -495 on the x-axis, and you'll be able to see several full cycles of the sine graph. If I click the window button, you can see the -495, the +495 is what it chose to give you that particular graph. So keep in mind, the point is, when you're finding suitable windows for your trigonometric functions, watch carefully whether you're in degree mode or radian mode, because the viewing window is going to be vastly different for those two. Okay, let's say a few words about rational functions. Rational functions are functions of the form of y is equal to some polynomial over another polynomial. Clearly, these potentially can be the most difficult types of functions to graph. Here we have an example, y is equal to 12 over x squared minus 4. I've already have it typed into the TI-84 calculator, but before I hit the graph button, let me just review a few things. And again, this is review for those who have studied rational functions. If you haven't, this might not make any sense to you. Don't expect to, I'm not teaching rational functions here. I'm just reviewing for those who've already covered that. All right. You recall that we could look at the denominator and we could immediately ascertain that there are two restricted values for x. Both 2 and -2 would give you 0 denominators. We can't divide by 0. 2 squared minus 4 is 0. So 2 and -2 are restrictive values. Those would be the locations of our vertical asymptotes. So if I could draw those vertical asymptotes a little better than I did before, we know we're going to have 2 of them, a 2 and -2. That's what we expect. In terms of horizontal asymptotes, we look at the degree of the numerator and the denominator. And if the degree of the numerator was greater than the degree of the denominator, like if we had an x to the 3rd power up here, then there would be no horizontal asymptotes. If the degree of the numerator was equal to the degree of the denominator, there would be a horizontal asymptote, and the function would be y is equal to a over b, where a and b represents the coefficients of the terms of the highest degree from the numerator and denominator. That's not what we have in this case. We have the degree of the denominator higher than the numerator, which results in a graph with a horizontal asymptote at y equals 0. So here we have y is equal to 0. We'll hyphenate that line there. And then we're going to have different sections of the graph. So we kind of expect either it's going to hug the graph here and then come up here, or perhaps down in this region down here. And in the extreme right values, we expect either something up here or something down here. Both of those are potentially possible. In between, we might have, there's only 4 scenarios. You know, if it starts from above, it may come back up above. Or it might start from above and then hug this other asymptote below. And if it starts from below here, it could, you know, rotate back down and hug this asymptote in the negative zone. Or if it starts below here, it could end up hugging this asymptote above. So we have a general idea of what to expect before we even hit the graph button. So if we're missing, you know, certain parts of the graph that we're expecting, then we'll adjust the window to make sure that we see what we're anticipating. Let's go ahead and hit the graph button to see if we have a suitable window. And sure enough, that is a suitable window. And that would be a good representation. Notice that that there is, right here at +2, we have a vertical asymptote. So this graph is getting closer and closer to that vertical asymptote. It's not going to cross over that, or not going to touch it. It keeps getting closer to it. And the same thing down below here. Now, maybe the most important thing I say about rational functions is to those who have older calculators. I started with a TI-81, then I used a TI-82, then a TI-83, and finally here I have a TI-84. But some of the earlier calculators, what they did would they would plot all these points and then connect them, if you were in connect mode. And so this last point that it graphed here would get connected to this point here. And so the actual, what you're seeing on your calculator isn't actually what happens. And for students who don't understand rational functions and the nature of asymptotes, they're deceived. And they, in their homework paper, they sketch a graph connecting these points just like their calculator did. But you know better, and I'm reminding you of that here. So if you have an older calculator, then don't do that. Don't connect those. Draw dashed lines for your asymptotes, and these blue graphs are not going to connect together. So there's a quick snapshot of rational functions. Okay, that's all the types of functions that we're going to cover today. Let me quickly summarize what we've hopefully accomplished today. We were able to graph functions on a TI-84 calculator. We know where the y=2 key is. We know how to type in the function. Sometimes introducing parentheses where the original question did not show any parentheses, but to make it equivalent to our function, we needed to introduce them. We've learned how to modify the color of the graph, the line thickness, change them to dashed lines, and so forth. We learned how to find suitable windows showing the x-intercept, showing all relative max and min points, showing all points of intersection when we have multiple graphs. And we understand that, we know that our understanding of these various types of functions will greatly help us with the window selection. We also understand that simply graphing functions is just the first step. The power of the graphics calculator lies in the tools and the utilities that we're able to utilize after the function is graphed and we've got a good window. But this is the first step. In my subsequent videos, we'll begin to see some application. We'll be solving equations and do some problem solving using graphs, and I think you'll find that very exciting. I have my email address at the bottom of the screen. I welcome your comments and suggestions for other math videos. Thanks for joining me.